Going on to topic 3 of chapter 3, zeros of a polynomial function. And again, some background might be in order here just to help you connect to what we're showing you. Now, when we look at a function, this is function notation. We said we can always exchange the function symbol with the letter y. So we would have y equals x squared plus x minus 2. And this is a quadratic equation that if we put this into our calculator, graphing calculator, it would look like this. It's a parabola that opens upward, and it's going to cross the x-axis at this point and at this point. Now, once again, at this point, what is your value of y? Well, on the y-axis, our value of y here is 0, right there. The origin is 0, 0. So the ordered pair of this particular point would be -2, 0, and this ordered pair would be 1, 0. So we have, in a sense, found the 0 values when y is a 0, what our x would be. So this is sort of the background of what we're going to look at as we, in topic 3, we're looking for zeros of the polynomial functions. And this is what they refer to. Now, back in an earlier section of our textbook that we didn't cover was a review section of factoring this quadratic equation. If we said y was a 0 and we factored that, we would get the factors from this, equal each of these factors to 0. Here x would be a positive 1, and here x would be a -2. And we proved it by the graph and through factoring. So this is one of the tools in our tool chest to find the zeros of polynomial functions. We're going to be able to factor it. Now, this will tie in to what we've just done in the previous section, that if we were using synthetic division to find out whether or not our factor of k here was equal to 0, that is, our remainder was a 0, we then have k as a factor. So let's take a look at this example. So here we see this is what they're giving, and we're wondering whether or not this is in fact a factor of this polynomial. Now, it will be a factor of this polynomial if we find that the remainder is 0. And again, we're thinking of our synthetic division. So let's move this up and do it. I've already shown you how to set this up, that if this is x minus k, what would k have been? Well, it was opposite sign. So if here it's a -1, then we're going to use a 1. And we're going to go through our process of synthetic division. And when we finish, we find that we have a remainder of 7. Since our remainder is 7 and not 0, we could say then that x minus 1 is not a factor of this polynomial. All right, let's take a look at letter B. Now, in letter B, we're looking at this polynomial, and we're saying, is x minus 1 a factor of this polynomial? Well, again, we use the technique opposite sign of our k value. Sometimes we think of it as c, and it would be a opposite sign positive 1. We go through the process of synthetic division, but now we end up with a 0 as a remainder. Since 0 is a remainder, this then is a factor of this polynomial. Okay? So then if we end up with this answer, and if we were to convert this from x to the 4th, this is now 1 degree less, x to the 3rd, plus x squared plus x minus 6. Let's see, am I getting enough places here? 3, 2. Well, taking a step back, this is what we had originally in B. This was to the 5th power. So this one would be to the 4th. Okay, I was misreading that a little bit. And so we have then that x minus 1 is a factor of letter B up here, since there is no remainder. All right, let's go on to example 2. Factoring a polynomial given a 0. So we're using lots of stuff from the previous lesson. As we look at this, we're saying, here is our function. And we're wondering if a negative 3 is a 0 of f. Well, we're going to take that negative 3. Now remember, it would be x minus k. So that would be x minus a minus 3, in a sense, keeping that in mind. We put it into our synthetic division of this, and we end up with our remainder of 0. Since our remainder is of 0, this indicates this is a part of the factor of this. But what was that original number? Well, in our formula, it's going to be the opposite of this, which makes it a positive 3. So that's where the positive 3 comes from. A little bit tricky. And if we multiply this by this, it gives us this up here. So x plus 3 is a factor. Now remember, the 0, though, was a negative 3. And the way we do this is we are looking for where this is going to cross the line. Now remember, if this is to the 3rd power, it's not going to be the shape of the graph is like this, not just this U shape here, parabola. So one of the points where it will cross the y-axis is at a -3. So this is one of the factors. And if this were 0, again, this part equals 0, and we could factor that, this would equal 0, and this would equal 0, each of these factors, then one of them, this x, is x equals -3, and this one is x equals, we transpose that, a -1/2, and this one is going to be a +1/3. Now, I don't have that indicated with this diagram, but these would be the other intersects. So it would be one there possibly, and then one right over there. Again, this diagram is just used for illustrative purposes. Okay. So again, you'll be doing some of these. This is the background behind it. Okay, we're now going on to the rational zeros theorem, which gives a method to determine all possible candidates for the rational zeros of a polynomial function with integer coefficients. These are whole numbers in a sense. Could be negative or positive, but whole numbers. All right, so what is the theorem itself? Well, they're saying this ratio of p to q, which is in a sense a fraction, in which p is the denominator, numerator I should say, q is the denominator, and they're saying if this value is a 0 of your function, then it's a factor of that function. And they give you a rather detailed proof that I don't think we need to memorize. Thank you. And basically it's saying here you're starting with your n power of something that is just one less. So this would be to the 4th, to the 3rd, and you're going down till finally you get to the constant at the very end. And they're saying once you get to this constant, if this constant is a factor, as we see right over here, 2, we could possibly use that in our thinking that maybe trial and error, by trial and error, whether or not we end up with a remainder of 0. Remember, anytime we get a remainder of 0, then that is one of the factors. Okay, we'll just put it in the form. So let's take a look at the first example using this theorem, where we see it's to the 4th power, and our last constant term is a 2. And list all possible rational zeros. Now, for this, we look at our ratio of p and q. Now, we're saying our q is this a to the sub 0, and that is 2. This 2 right over here. And our lead coefficient is 6, which is up here. A to the sub 4, right there. Now, when we make a ratio of these numbers, it could be plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6. And if we have it this way, we could also possibly have some fractions that they're describing here. And then we're going to use the remainder theorem to show that 1, through trial and error, is a 0. So as we set it up, we're saying 1. But remember, that 1 is x minus a minus 1, so that in its formula, we will use the opposite sign. Well, let's again take a step back, and the formula is x minus k. So what would k have been that we're going to use in this particular formula? Remember, we said it was, the shortcut was opposite sign. So there's where we get the 1. But remember, that is going to be originally an x minus 1. So we're getting the positive 1 from our k value. Okay, we do our synthetic division, and we end up with a 0. So 1 is a 0, but the factor that 1 comes from was this, opposite sign again. So this we said was equal to 0. So again, x equals 1, which is what we're saying. Now, we then have this value that we put into synthetic division, and we're wondering now if a negative 2 is a factor. So we put our negative 2 in, we do our synthetic division, and we end up with this. And 0 is the remainder, so this is a factor. Now, what would this be? Remember, opposite sign. So this is going to be k plus 2. So far, we have 2 factors. We have this one and this one. So I'm going to move it down, and we'll see these 2 factors, and we have this left. So this was our first one, this was our second one, and this is what we had left from our synthetic division, our second time, which is this. So if we were to FOIL these and then multiply it by this, we would have gotten our original up here. Now, if we plotted this using a graphing calculator, this is what our graph would look like. And notice we have found one of the zeros here, a negative 2. We also found a positive 1, which is right there. So we found 2 of the zeros so far. And now if we look at this trinomial, this can actually be factored into this and this. So if we factor this, we get a positive 1/3, which is right there. And we're going to get a negative, as we remember, we're equaling each of these to 0, and then solving for x. This becomes a negative 1/2, and there it is right there. So this was an equation to the 4th degree, and we used the remainder theorem to start to give our factors, and it is quite a tedious way to get things done. But you'll have your practice and hopefully your quiz me's to develop your mastery. Now they are giving us a very important caution here. It says the rational zeros theorem gives only possible rational zeros. It does not tell us whether these rational numbers are actual zeros. So you must rely on other methods to determine whether or not they are indeed zeros. Now, suppose you have a function that looks like this with fractions. So you might say, how do I do that? Well, the old rule of making it a larger equation, remember this is going to be a 0 over here, because that's what we're looking for, the zeros. To get rid of all our fractions in our denominator, the technique is to multiply each term by the lowest common denominator, which as we look at this is going to be 6. So if we multiply each, we're multiplying that 0 by 6 as well. Here, nothing cancels out, so we get 6x to the 4th. Here the 6's cancel out, and we get a negative x to the 3rd. Here the 3 goes once, goes into there twice. This gives us 4x to the 2nd. Here the 6's just cancel out, and we get a negative 1x. Here the 3 cancels, with the 6 we get a 2. And there's our new equivalent equation that instead of having fractions in it now only has integers as coefficients. So the number of zeros. The fundamental theorem of algebra says that every function defined by a polynomial of degree 1 or more has a 0, which means that every such polynomial can be factored. Okay, this looks like my good old friend Descartes there, or Descartes. No, that's Carl Friedrich Gauss, another mathematician back in there. All right, I'm getting mixed up on my mathematicians. Okay, so every function defined by a polynomial of degree 1 or more has at least one complex 0. All right, let's go on. Well, in earlier courses, I would define this as, let's say if you have x to the first, you're going to have one answer, or in a sense, 1 0. X to the second, 2 answers. X to the third, 3 answers. X to the fourth, 4 answers. And sometimes these answers are the same. So only write it once, but theoretically coming out of the system. And I guess this is what they're describing as the number of zeros theorem. So depending upon what degree your equation is, you will have that number of distinct zeros. All right, let's go on. Let's look now at example 4. Finding a polynomial function that satisfies given conditions, that is, the real zeros. So they're giving us the zeros of a -1, a 2, a 4, and in a sense giving us this qualifier that f of x, where x is 1, y equals 3. Okay, we'll get to b shortly here. So basically, these are the results. And when we go to put this in its factored form, we have 3 answers, so we have, in a sense, 3 factors. And here, this would be opposite sign, x plus 1. This is going to be x minus 2. And this one would be x minus 4. Now they give us this down below, but we still don't know one of the concerns, which is a. So we have this, and we say this is going to equal 0 over here, as this is. But we want to find out, suppose now, that we know something of this. We know here that x is 1. So what we're going to do is wherever there's an x here, we're going to put a 1. So a 1 there, a 1 there, a 1 there. So this becomes a 2. This becomes a -1, and this becomes a -3. So we now have, and then they have this down here in this line, we have 2 times a -1 times -3. This is a positive 3 times 2 is 6a. So we then have 3 equals 6a. So we're now going to divide both sides by 6. And we get a equals 1/2. So right over here, we're going to put 1/2 there. And that's going to give us our equation once we multiply through. So let's take a look at it. So there's our 1/2. And we have these 3 binomials that we're going to FOIL and multiply. And then multiply everything by 1/2. And this is what we end up with. Wow. Again, it's rather tedious, and you don't get to master it until you try some of these. In example B, here we only have one value. Our 0 is a -2 and has the multiplicity of 3. And we have this, and I'll have to raise it up so we can see what it looks like on our next page. So with the multiplicity of 3, that means our factor, where our 0 was a -2, here it becomes a +2, and we have that 3 times. And it's then this to the 3rd power, and we still need to find out what a is. Well, we have x as being a -1, and our y as being 4. So we're going to put a -1 there. That's our x value, the -1. And this becomes then a +1. 1 to the 3rd power is 1. So we're left with 1a, that we're putting the a over on this side. A equals 4. So again, we can expand that to the 3rd power, and we're going to multiply each term then, once we have expanded that, by 4, and that gives us this answer. Again, some pretty tedious stuff here. We're now going to look at some complex numbers, the conjugate zero theorem. And once again, a very helpful thing that we've developed in the past is the concept of a conjugate. Well, we first looked at that a long time ago, A plus B. What is the conjugate of that? Well, it's A minus B. That is, just the middle sign is reversed. So if we were to FOIL this, when we FOIL conjugates, the middle terms cancel out. So we get A squared minus AB plus AB, our outers and our inners, and then a minus B squared. So our middle terms just subtract out. So whenever we multiply conjugates, we end up with the difference of perfect squares. This is very useful in doing imaginary numbers, because anytime we have an I squared, which will come out of this, this is equal to a negative 1. I squared by definition equals negative 1. And then we convert from imaginary numbers into real numbers. So here they're just going over the rules that I've just described when we think of conjugates. And here they're indicating Z is this, then its conjugate, which is a bar over the Z, is its opposite sign in the middle. Okay? So we'll keep that in mind. So the conjugate zero theorem, if our function of x defines a polynomial function having only real coefficients, and if we have z, this is one of the conjugates, then the conjugate of z is just its opposite sign. Check it out here. And they do give us a proof, which is kind of challenging. So when the conjugate zero theorem is applied, it is essential that the polynomials have only real coefficients. All right, let's go on. Example 5. Find a polynomial function of least degree having only real coefficients and zeros. So we have 3 and 2 plus I. But in order for this to have a real number coefficient, we have to also include its conjugate, which is x minus I, or in this case, 2 minus I. Okay, so here are the set of factors. We're using brackets because this and its conjugate are in parentheses. We clear parentheses, we FOIL this, we get this, and we get that, and we multiply that through, and we end up with this. So again, the background here is to know that you had to use a conjugate in order to get x squared, which would give you, I should say I squared, that would give you a negative 1, which changes it from imaginary numbers to a complex, to a real number. All right, Well, again, the work is here, and I'm not going to take the time to go through all the stages. A few more definitions. I'm not going to read them aloud because that would just take time. But keep in mind that in some cases, if you have an answer that looks like this is a complex number. It's not a real number. So there may be times when you have no real zeros. That is, you have answers that look like this, but they're not real numbers. In example 6, they're asking you to find all zeros given 1 0. Here, they're giving you this polynomial function, and one of the zeros is this, which is an imaginary number. So you're going to put that as one of the factors, and remember it's opposite sign, but since it's x minus k, then our k value is this, and we're going to use synthetic division to start us through. And we leave lots of places because that was one we had in an earlier lesson, and we end up with this. Now, by the factor theorem, since this is one of our factors, you can then write it this way, and get some additional synthetic division where this is again a 0. You get the other factor, and then factor this, which is nice for a change, and you end up with 4 zeros. 1, 2, 3, and 4. And maybe we won't give you, or your teacher won't give you any of this hard to do, but these are challenging. All right, let's go on to our last little section here, which is Descartes' rule of signs. So you can read this through. May have to pause it, and then we'll get on to doing it, where if you have 1, 2, and 3 changes of signs, you end up with 1, which is an odd, and 4 negative zeros. Consider the variation of the signs, and since there's only one variation of signs, you only have exactly 1 negative real zeros, or 0. And if we were to graph that, we'd see there's only 1 negative 0 here and 3 positive zeros. And I went through this very quickly. You're going to have to read that. This is almost 40 minutes long, and I was trying to keep it short. But there's a lot of stuff, and good luck. This is just a little quick review for you that wasn't too quick after all.